Thank you. I'm really happy to be able to present the work that we did on the nucleation and growth of bismuth oxychloride nanoparticles tested by in situ pair distribution function and also in situ liquid cell transmission electron microscopy. This was the final work of my PhD. It was a collaborative effort between Indiana University and the University of Copenhagen. It can be found at this nanoscale reference here. So the motivation for our work is driven by solar water splitting, where you use light with energy greater than the band gap of a semiconductor that photoexcites charge carriers that can then be used to split water into hydrogen and oxygen. Typical materials for solar water splitting have been oxide-based materials. The first tested was titanium dioxide. But titanium dioxide and other oxide materials suffer from very large band gaps. For example, if you compare the band gap of tantalum oxide to tantalum oxynitride to tantalum nitride, you'll see that the band gap is very wide for tantalum oxide, almost 4 electron volts, something that is very UV absorbing only. But as you incorporate a secondary anion into this, so tantalum oxynitride and tantalum nitride, you begin to shift the valence band maximum upwards so that you get a smaller band gap and thus can absorb more of the visible light. And so bismuth oxyhalides also have this similar property whereby tuning the halide composition, you can tune the band gap from something that's only UV absorbing to something that absorbs well into the visible range. Bismuth oxyhalides also have some unique crystallographic properties that makes them good for this photocatalysis work. They are a layered material composed of alternating positively and negatively charged layers. And these charged layers create an internal static electric field between the positively and negatively charged layers, so that when you photoexcite holes and electrons, the holes preferentially migrate to the negatively charged layers and the electrons migrate to the positively charged layers. And so that separation minimizes recombination and provides a 2D path to the surface for the charge carriers, improving charge separation and minimizing that recombination. And so bismuth oxyhalides can be made actually remarkably easy, but I like to say they can be made very easily, but they're very difficult to make well. And what I mean by that is when you take a simple salt like bismuth trichloride, dissolve that in water, you will immediately get out a precipitate of bismuth oxychloride as a solid precipitate. However, when you do this, you are often limited. You have polycrystalline products, poor morphology control, and large aggregates. And so to be able to make controlled nanomaterials of these bismuth oxyhalides, we need to kind of rethink how we do these syntheses. And so in summarizing this, Lizzie Zhang's group wrote in a review, the great challenge for the preparation of well-defined structures is the very fast nucleation rate of bismuth oxyhalides in aqueous solutions. And so this great challenge kind of became a main focus of my PhD work in trying to come up with unique ways to slow down that nucleation and growth rate. And so to be able to come up with these controlled morphologies, we wanted to kind of rethink what our precursors were. And so thinking about our bismuth source, we want this to ideally be something that is water soluble, relatively inexpensive, unreactive in ambient conditions to allow for that controlled nucleation and growth. Unfortunately, however, common bismuth salts are not soluble. So if you take something like bismuth nitrate, bismuth trichloride, immediately they hydrolyze in water to form these solid precipitates, bismuth oxychloride, again, with poor morphology control. And so we found in the literature from the early 90s this paper that used lactic acid as a bidentate ligand to coordinate to bismuth, and it formed this bismuth lactate complex that was water soluble. So having a water soluble bismuth source was certainly useful, but then trying to add in the halides to this, adding in a simple halide salt, sodium chloride, potassium bromide, we immediately broke down that complex to form precipitates. We tried different oxidation states of our halogens to try to get those co-soluble in the same solution. Those didn't work. And so early in my PhD, I had this challenge that I needed a halogen source that doesn't readily release halide ions. And after struggling with this for a bit of time, we came up with the idea of using small organohalide molecules to be able to incorporate a halogen into our synthesis without it being a halide ion. So all of the ones shown here have been used in our synthesis. The two boxed ones, 2-chloroethanol and bromoacetic acid, proved to work the best. And these function, they're sufficiently water soluble, but they don't react with water at room temperature to yield a halide ion. So that made it work in our syntheses. And so in our very first paper, we were able to show that we combined bismuth lactate complex, these organohalide molecules. We used an inorganic salt flux, and we did this in an aerosol synthesis method. We were able to make the nanoparticles shown here, where we have bismuth oxybromide on the left, bismuth oxychloride on the right. They were phase pure oxyhalides, single crystalline, as determined by selected area electron diffraction, and were overall demonstrated to be useful photocatalysts in that paper. We wanted to understand how this was working. However, we had a precursor system that worked, but we didn't necessarily know exactly how everything was taking place mechanistically. And so bismuth and halide ions, we kind of started with this guiding principle. Bismuth and halide ions readily precipitate as BiOX in these aqueous systems. And we had a bismuth source. We didn't know how we were specifically generating halide species in our system. So we drew on the chalkboard. You could potentially think of water as not only the solvent, but a reagent. Halides are good leaving groups. You could envision a sort of organic reaction, SN2 type reaction like this. Before all the organic chemists come at me in the comments, though, I do want to point out some specific findings that we thought were important here. One of the driving forces for this is, even if this is an equilibrium that very much does not favor the product side, as we are releasing that halide ion, that halide is then immediately reacting with our bismuth source to precipitate out as bismuth oxybromide. And so even with a poor equilibrium, Le Chatelier's principle is driving this reaction forward, which helps our reaction. And so another thing that makes this particularly useful for controlled nucleation and growth is that we can control the rate of this reaction by using temperature as a synthetic lever. And so temperature, by increasing the temperature, we can speed up the rate that a free halide is released. And then as soon as that halide is released, then there's a fast reaction with our bismuth source to precipitate out. So by controlling the temperature, we can control the halide formation. By controlling the halide formation, we control our nucleation and growth of our product. So that's something that we definitely wanted to see in our system. And so then moving into a second paper in my degree, we took a step back and we realized we had these organohalide molecules alongside a bismuth lactic acid complex. And so one of the areas of the literature that I've been reading about are these single source precursors, which have a lot of industrial applications, compatibility of different incompatible functional groups. And so I thought, can we combine these? Can we make a bismuth halolactic acid complex where our halogen atom is directly built into the bismuth complex? And so we were able to synthesize these molecules, which are derivatives of the lactic acid that we had in the previous paper. We reacted them in a 4-to-1 ratio with our bismuth nitrate, and we were able to achieve these complexes shown here. We were able to solve the crystal structures using the support of our crystallographer, Dr. Maren Pink. And these were then used in further applications. We wanted to demonstrate them in a variety of applications. First, we did colloidal synthesis, heating up these precursors in an oil bath, produced bismuth oxyhalides with good morphology. We used a spray pyrolysis method, spraying that aqueous precursor onto a heated substrate, was able to make thin films. And also heating up those solid precursors, they were able to decompose into bismuth oxyhalides with elevated temperature. And so that was a pretty useful way to kind of show we had single source precursors that were able to react in a very similar way. to make these bismuth oxyhalide products. And so now getting towards the TEM work that I know you're all here to see, we realized that we had a very unique opportunity here where by controlling temperature, we could really control the formation rate of this product. As we alluded to earlier, the great challenge of slowing down that nucleation and growth rate, we realized we had a unique way to now slow down the timescale of the bismuth oxychloride formation using temperature as that lever. And so we were able to open up new capabilities to study this nucleation and growth in ways that were not previously possible. And so briefly, I'd like to just discuss what the literature says currently about the nucleation and growth method. This has not been tested, but this is kind of the hypothesized way. And so just a little cartoon here, we start with bismuth hydrolyzing in water to produce these Bi2O2 positively charged species. We then have them bind together with chloride ions to produce this more neutral nuclei. Those nuclei then begin to assemble in the AB plane to lower the overall surface energy of this layer, and then those layers stack in the C direction through van der Waals forces, forming our overall BiOCl crystal structure. But this has been a hypothesis that makes logical sense, but it hadn't been able to be tested really yet. And so we thought we were using our set of precursors that we had. We thought we had a good way to be able to test this. And so we wanted to test this using two complementary techniques: pair distribution function with in situ heating, and then liquid cell TEM, again with in situ heating. So looking first at our pair distribution function work. Pair distribution function, just to give a brief overview of it, it can be thought of as a way of mapping the rate, the distance between any two pairs of atoms in a crystal structure. So if you look at this simple sheet of graphene, you might take this as your center atom. You'll see that there are 3 atoms at 1.42 angstroms. You go another distance out, there are then 6 carbon atoms at 2.46 angstroms. And then as you be able to build this out in radial distance, you can start to get a plot that gives you the probability of finding another atom at a distance r from a given atom. And so looking at this, the atomic distance is our x coordinate, our peak position. Our peak area is the abundance of that distance weighted by the z of that atom. And then the peak width corresponds to the disorder of that distance, and so on. And so we thought with our precursor that we had, we would then be able to heat it up, form our bismuth oxychloride crystal structure, and then be able to monitor the X-ray total scattering to get out this maybe some insights into what's happening between our reactants and products here. So this work was done at Petra 3 beamline in Germany. We started the experimental setup. We had our solution heated up in an aluminum block with X-rays passing through it that were the scattering was detected. And so before we did any heating, we looked at our precursor complex in solution. Our precursor, this was our experimental collected data in dark blue, and in purple was our calculated data. The calculation shows that we should have these humps here with our corresponding to the different bismuth, oxygen, bismuth chloride distances, and so on. And we saw a pretty similar, there was some good match at some of our longer distances. Those start to kind of fade away a little bit. That's due to the rotation of the different bonds as you get out to that second carbon here. The rotation of the bonds makes those distances less rigid as they would be in the solid state. We also noticed that in the solid crystal structure, our bismuth oxygen distance, both oxygens of the ligand were about the same at about 2.4 angstroms. But in the liquid phase, we saw that those kind of started to separate into two distinct bismuth oxygen distances. But overall, we still had a mononuclear complex with a slight wider range of those bismuth oxygen distances. Then, as we started to heat this up, this is first in reciprocal space. As we heated up we heated up 3 degrees a minute from room temperature up until 90 degrees, and then held it at 90 degrees. As we heated up from room temperature, you'll start to see just what looks like the precursor complex. And then as we get into our later heating time points, you'll see these characteristic peaks arise of our bismuth oxyhalide. Looking at that same data in real space, we were able to map that to specific intra-layer and interlayer bismuth-bismuth distances. The bismuth-bismuth distances are particularly noticeable just due to their bismuth's very high atomic number. And so we were able to break down this data and look at it. One of the things we saw was that we went from precursor to product without any noticeable intermediates, which was a very unique finding that kind of showed us that our original hypothesis was on a good track. No obvious intermediates was one of the major takeaways from this portion of the paper. We also then looked at the very end of our heating, comparing our experimental pair distribution function with our calculated pair distribution function. You'll notice that at the longer distances, the match turns out to be a lot better. And so we took a difference between our experimental and our calculated value that's shown here in gray. And you'll then notice that the calculated difference curve very much matches our starting material before we had any heating applied. And so this shows that at the end of our heating experiment, we had bismuth oxychloride peaks, along with a significant amount of our starting material, unreacted starting material remaining. Another thing that we monitored as the heating occurred were the lattice parameters of our BiOCl crystal structure. One of the things we noticed is that our it's a tetragonal crystal structure, so our A and B lattice parameter was very steady at 3.88 angstroms, showing that in the AB plane we weren't changing much on the crystal structure. But then our C parameter, we noticed with extended heating, did shrink a little bit from about 7.515 angstroms to 7.489 angstroms. And that shows that in the C direction, so vertical on the crystal structure on the right, we were able to experience some contracting. Likely this is due to potentially water molecules being excluded, or our layers being able to kind of sit nicely on top of one another, excluding any other ions or water from the crystal structure, showing that we get much closer towards the dried state lattice parameters. And so our in situ pair distribution function with in situ heating shows the formation of bismuth oxychloride upon heating the mononuclear bismuth chlorolactate complex without any obvious intermediate phases forming. We can't exclude potentially other things happening that wouldn't be seen in the time scale of our measurement, but everything we saw does support the original theorized hypothesis of how these form, but now we're able to support that in an experimental method. And then getting to the liquid cell TEM work that I know the audience here is excited to see. We wanted to do the same experiment of heating up our precursor, now be able to watch those particles form in real time. So just a quick background on the liquid cell TEM. We take a very small drop of our sample solution, sandwiched between a small E-chip and a large E-chip on top. This all gets sandwiched into the very tip of the TEM holder, which goes into the instrument, allowing you to have a very thin region of water that is not then exposed to the vacuum of the inside of the TEM. For our experiment in particular, we used these large chips that had a resistive coil in them. So those electrodes could be connected to the holder, where the the application of electricity here could then be used to heat up our sample to a desired temperature. And so we were able to then watch the nucleation and growth as we heated this up. I'll show here a video of the nucleation and growth happening. It's going to go quite fast up until about the 6-minute mark as the temperature heats up. After 6 minutes, we'll slow it down slightly, and you'll be able to see this kind of one moment where you just have burst nucleation right there. And so that burst nucleation happens. We then see particles can move around slightly. You'll see some of them become thicker and thus darker. And often we get more square and rectangular plates that form, and the square and rectangular morphology is due to the crystal structure, has a preference to form these plates. I'll show that one additional time where this black box here shows the stills at the left as these products are forming. So it happens just after 6 minutes here at about 53 degrees. We see that burst nucleation, and then the particles become more square and rectangular, and also some of them darken as they become thicker in the C direction. And then one last thing, I'll show you just this region here so you can see the video that these are specific time points of. We can see a particle start to form there. It gets thicker as it goes with time, leading to a darker contrast, and you see this very square plate morphology develop. So after we were done with our heating experiment, we were able to do STEM elemental mapping, showing that we had bismuth, oxygen, and chloride within our particle. You'll notice oxygen outside of our particle. This is due to the presence of oxygen in water. Selected area electron diffraction shows that we had single crystalline bismuth oxychloride, indexed as shown. And then we were also able to do STEM videos. STEM has a better contrast at those very early nucleation and growth stages. So using that better contrast, we were able to do a second video where we still images are shown from left to right, and then on the right here is this video as those images come in. We were able to use particle tracking to get these three nuclei that formed very close proximity together, a couple nanometers away. But one of the things you'll notice is that they form at slightly different times and different growth rates. So you'll see that maybe this middle particle grows in last. That top particle seems to grow in slightly more in the middle, but it grows fast. And this bottom particle kind of grows in a lot steadier from the beginning of the heating. And so kind of the big takeaway from this is that we had these different nuclei that form. They all kind of end up in the same spot, but they kind of take slightly different trajectories to get there. And then kind of just to wrap this up, we think back to our initial this challenge that we wanted to set out and tackle for the preparation of well-defined structures for bismuth oxyhalides that was limited due to this fast nucleation rate. And by coming up with these precursors, we think we were able to develop new opportunities for the controlled aqueous synthesis and to be able to study these the nucleation and growth of these photocatalytic materials. From our experiments in this last work, the in situ PDF and liquid cell TEM, key details of the formation and growth of bismuth oxyhalides were found, including no obvious intermediates and a variable particle development as temperature increased. And so with that, I'd like to thank all the folks who helped make this happen. All the authors are shown here on the left. Laura and I are co-first authors on this paper. I led the liquid cell TEM half of this paper, and Laura was instrumental in getting the paired distribution function analysis done. Jack Ugasian helped with some of the image processing. Yetta Matheson helped with the PDF portion. She was actually a visiting student in our group who kind of I think made the connection between Kirsten's group and my boss Sarah Scrabblex group happen. Shun and David Morgan are electron microscopists who helped a lot with this, and our advisors, Kirsten and Sarah. Our facilities, Electron Microscopy Center at Indiana University helped considerably. Beamline P21.1 at DESI in Germany, and then the Molecular Structure Center and the Nanoscale Characterization Facility also supported this work. It was funded by the National Science Foundation, yet it was supported by the Willem Fonden, and travel arrangements were supported using the Danish scattering fund. I'd also like to thank Protochips for their support in helping us complete this work. Liquid cell experiments are non-trivial. I'd like to especially thank Madeline Dukes for helping us troubleshoot some of our early experiments and helping us get this work completed. If you're interested in reading the paper, here's a QR code and the reference information there. If you'd like to connect with me or ask questions about this work, my contact information is there on the right. And thank you all for listening, and please reach out if you have any questions. Thanks.